What we're doing today is a one-way analysis of variance. ANOVA is the abbreviation for that. This comes from section 5 of chapter 10. And the difference between this problem and some of the ones we've done before is that we have several populations. That means 3 or more. They're assumed to be independent random samples. They're normally distributed populations. And we are assuming the variances are equal in order to do this one-way analysis of variance. Now, we're actually going to test that using the Levine test or an alternative method, but we'll show you that when we get there. Okay, this is example 1016 on page 356 of the text. This is what it says. To test the comparative effectiveness of 4, notice we have a sample of size 4, in-store locations, you conduct a 60-day experiment at 20 same-size stores that have similar store-wide net sales. So, 4 locations, different places within the store. We have 20 stores that we're examining, and so we have randomly assigned 5 stores to each of the particular locations. At the end of the experiment, you organize the mobile electronic sales data, that's what we're looking at, by group and store the data in mobile electronics. So the unstacked data, which means we've taken it from just a single column, which is the way it appears in the file initially, and put it into more than one column, 4 columns in this case, along with the sample mean and sample standard deviation for each group. So here's what the data looks like. All right? So we've got 4 different locations, in aisle, front, kiosk, and expert, and we have 5 values for the mobile electronic sales at each of these locations. And what we want to know basically is the average level of sales the same regardless of which location we place the mobile electronics. For the original in-aisle location, for instance, the mean sales were $29.982 thousand. This is $32,000, $31,000, and $31,300. And these are the standard deviations that correspond to each one of those values. So we go through our 6 steps. State the null and alternative hypothesis. We've observed the 4 sample means being different. I'm going to use the F-test among more than 2 means to determine if the sample means are sufficiently different to conclude that the population means are not equal. That's what we care about, is the population means, not the sample means, which is all we have to work from right now. The null hypothesis says mu1 equals 2 equals 3 equals 4. The alternative is not all means are equal. So we could write it does not equal for each of these, but it really means at least one pair is not the same. Step 2, choose the level of significance and the sample size. So we've got a sample of size 5 for each one of the locations, and alpha equals 0.05. What test are we going to use? We're going to use analysis of variance to allow us to compare multiple populations or groups. Okay, more than 3 or more actually. In ANOVA, you can take samples from each group and figure out whether there is a significant difference among the groups. Figure shows differences in the sample means, so we're going to use ANOVA F-test. Again, the assumption here would be what? Independent random samples, normally distributed populations, and equal variances. We're trying to find the critical value next. So what we do is we look in our table for F critical values. We want the upper tail area to be 0.05, and so we're only going to reject if we get a large value, a value larger than the value we find in the table. All right, so in this particular case, we have 3 degrees of freedom in the numerator, and that because we have 4 groups, columns minus 1 is 3, and then we have in the denominator 16 degrees of freedom, which is R times C, R minus 1 times C is how we find that. So number of rows, 4 times C is 3. R minus, excuse me, I'm having trouble with that. All right, degrees of freedom for the denominator is rows times columns minus number of columns. Okay, so that gives us 16 degrees of freedom in the denominator. So we look at our table. Remember, you have to keep the denominator degrees of freedom on the left side and the numerator on the right side. So we get 3.24 as our critical value. Step 5, we examine the F value, F statistic, which is provided in the printout. Under the ANOVA section, between groups, 88.21, and we're using a 0.05 level of significance. These are the sample averages, the sums for each column, and the variances for each column. We have 5 in each group, as we've said. So we've got a pretty large F value there. And here's N, that's the total number of observations, which is 4 times 5, minus C. That's where the 16 came from for the degrees of freedom right here. Is N minus C, where N is the number of rows times the number of columns minus the number of columns, which is 4. So that's how we got 16. 3 and 16 is how we found our critical value. Over here, remember, 3 and 16. So you can find it on the table here too. Between group variation, within group variation gives us the degrees of freedom. Okay, my critical value, as you saw on the previous slide, was 3.24. We can also see that on the printout. 3.2389 is what they actually say right here. Notice the p-value is equal to 0. So that means we're going to be highly confident that it does appear that there is something different going on here. Okay? In other words, all the means are not the same. It does seem to matter where we put our displays. Enter the upper tail critical value, okay, 88.2122 is greater than 3.24, so we're going to reject the null.